Okay, we're sticking on the load side, but now we're going to focus on connecting to feeders. Feeders. So what is a feeder? It's defined in Article 100. A feeder are the conductors between the service or primary source and the final branch circuit overcurrent protection devices. Okay, so let's take a look at our diagram. We've got our primary power source coming in. We've got our main panel. There's our main breaker. Here's some branch circuit breakers. And this I would call a feeder supply breaker. It is some size. It's protecting these wires. And this feeder is running to a sub panel. And then in that sub panel, we have our branch circuit breakers. And in this case, we actually got an inverter connected in that sub panel. So we talked about the rules to consider to make sure that this bus bar can handle the combined sources of here and here. And we also can apply those rules in the main panel. Presumably, if the feeder has been incised and installed correctly, it's going to be coordinated with the size of the breaker and the bus bar. And so if we're good with the bus bar, we should be good with the feeder as well. Here we're connected at the opposite end of the feeder, right? And the feeder comes in, supplies this. We're all the way at the very end of it. Now, one thing I do want to mention is the main breaker in the sub panel here is not required. Not required. You may have one there because it's nice to have a main breaker sometime and be able to shut the whole panel off. But that circuit is already, and that bus bar are already being protected by the supply breaker for the feeder in the AC main service panel. Okay. Now we're connected at the opposite end of the feeder. We've talked about the rules to address this. We want to kind of look at what happens when we're not at the opposite end. So load side connections to feeders, but we're not just connecting in that sub panel there at the end. Now, so what we're really focusing on is a power source output connection made to a feeder somewhere other than the opposite end from the primary OCPD. So with the picture we just looked at, we were at the opposite end from the primary, right? The feeder supply breaker in the main panel, we were connected in the bottom of the sub panel, all the way at the opposite end of it. What happens when that's not the case? Well, and then we need to consider the possibility of overcurrent due to overlapping current on that feeder conductor. So let's take a look at our diagram and then we'll kind of build on it from here. We've got our primary power source coming in through our meter, our main breaker, 1000 amp in this case. We've got some breakers going to other feeders. We're going to be looking at this one on the bottom here, supplied by a 200 amp overcurrent protection device, our feeder supply breaker, and it runs the feeder to what we call a main lug only sub panel. So as I said, don't have to have a breaker here. Sometimes it's cheaper to not, and this only has lugs. So we bolt our wires in there in the terminations, and there is not a main breaker. There are breakers for the branch circuits, of course, and the feeder is protected by the breaker in the main panel, but there's not one at the end. So very common, main lug only sub panel. So we got to consider the current from both sources, the possibility of overlap. So I've got a 200 amp feeder. It's got a 200 amp supply breaker. It's running to a 200 amp bus bar in this panel. There's loads in the panel. Yeah, the load breakers are more than the bus bar rating, but that's common and true for most panels that you're going to run into. There's no PV system involved here yet. What happens when we do connect one and we connect it not at the opposite end, but somewhere along the length of that feeder? So this feeder, maybe it's running, from ground level up to a sub panel several floors up, and we're going to tie into it and interconnect to that feeder along its length because it's much more convenient. Or it could be, run across a building and it's just easier to get at that feeder. Whatever the situation may be, well, now we've got, as always with Article 705, we've got multiple power sources. We're interconnecting. We're still on the load side, but we've got to consider what's going to happen to that feeder downstream from where the PV system is interconnected. Okay, so there's our section of feeder and bus bar that now could see overcurrent, right? To the left of there, what's happening? Current's coming from the main, no more than from the main supply, feeder supply breaker, no more than 200 amps. It's protected by a 200 amp breaker. Maybe some cases, depending on what's happening in that sub panel over here and what the PV system is making, well, I may be pushing current back. I could pull 200 amps this way, but let's say all of these breakers all of a sudden want to pull full power. Normally, what would have happened? 200 amps, trip. I can't pull 300 amps through these breakers because this is going to limit it. It would trip off. Well, what do I got now? I could pull 200 from the main, from the utility, And with this PV system, I could pull the other 100 that I need. I could pull that other 100, and all of a sudden this 200 amp feeder, which was sized correctly to begin with, now could see more current than it's rated to handle because of that connection of that second power source. Right? The current overlap is where the issue comes in, and we need to deal with that. The PV system is connected to the feeder, but not at the opposite end, thus giving the opportunity for current to combine from the two power sources and overcurrent that feeder, and for that matter, the bus bar in that panel, that subpanel. That subpanel is only rated for 200 amps. So now it's at risk as well. So how do we deal with this? 705.12b1a gives us the first of two options. We can make sure that the ampacity of the feeder on the load side of the power source connection is greater than or equal to the sum of the feeder supply breaker plus our new power source, and that's our good friend Imax times 1.25. Right? In this case, we've got a PV system that has a rated continuous output current of the inverter of 144 amps. It's connected through a 200 amp breaker, and we need to make sure that to the right of that, right, on the load side of this connection, that this feeder and the bus bar is able to handle that second power source. Okay, so how do we do that? First option is to make sure the wire is big enough. That sounds easy. It can be really difficult in the real world because we may be pulling conductor out, could be running it, as I said earlier, up a couple of floors, all the way across a big building. Who knows? Maybe it's easy, maybe it's not. It's going to depend on the particular scenario, but the math is pretty easy at least. We take Imax times 1.25, 144 amps times 1.25 gives us 180 amps. We add that Imax times 1.25 to the feeder supply breaker. That's 200 amps in this case, 380 amps. That tells me what the feeder and the bus on the load side of that PV system or inverter interconnection need to be rated for. So I need to increase the wire size. If it was rated for 200 amps before the PV system showed up, which was probably the case because that's the supply of the feeder breaker, well, now it needs to be bigger. It needs to be rated for 380 amps. That bus bar, there's no main breaker in that panel. That bus bar is also going to need to be protected. 380 amps is the calculated value. 400 amps is the common size that you'd probably end up using. So that's one option. The other option, kind of like with our feed-through conductors that we looked at earlier, is to reestablish overcurrent protection at the point where the PV system is connected. If I put a breaker in there that reestablishes the overcurrent protection at the level that the system was originally designed for, and it's less than or equal to the ampacity of the feeder, then I'm going to be protected once again. Super easy to drop in on the PowerPoint. Bam, there it is, 200 amp breaker. Add a 200 amp breaker on the feeder on the load side of the inverter connection. Now, regardless of how many power sources are upstream from there, it can still only pull 200 amps. That feeder that was previously rated at 200 amps, protected. Bus bar in the sub panel, protected. We're good to go. This can certainly be done. It often requires new enclosures and additional equipment, but those are the two options. Make the wire bigger or reestablish overcurrent protection. What does that sound like? It kind of sounds like the same options we had when we dealt with panels supplying feed-through conductors, and that's because the logic is exactly the same. Is there a spot or a length of conductor or a bus bar where current can combine from multiple power sources? If so, it's either got to be big enough to handle it, or we need to reestablish overcurrent protection so that it's protected at a level of current that it can handle. Okay, that's feeders. We'll switch and talk about taps in part 8. Talk to you soon.